Good morning, everyone. Uh, Today I am going to uh, give presentation about topic on critical section and problem solutions, which is my assignment, and I am the student of PICT fourth semester. So let's begin my presentations. Uh, this is the introduction about the critical sections, problem and solutions. Uh, First, why does this problem exist? This is an introduction. In a modern OS, multiple processes run concurrently, currently and often share resources, variables, files, memories. If if two processes modify the same data at the same instant, the result depends on timing. Timing. For example, two processes increment count 5. P1 and P2. Uh, the example on the slides show this clearly. P1 and P2 both read a counter at 5, counter at the 5, both write 6, but we expected 7. 1 increment is lost, and this is a rest condition, and this is a problem. Uh, the segment of code where a process and modified share resources and data is called a critical section. Coordinating access to it is the critical section problem. And we are going to second slide. uh, Anatomy of a process. Every process is structured into 4 parts around its critical section. um, the entry section. Entry section. First one is entry section. Entry sections request permission to enter. On second section is a second process is critical section. Critical section. The critical section is where said data is modified. The third one is exit section. The exit section signals other process it has finished. And last one, remainder section. The rest of non non-critical codes. The exit section signal that the process is done, uh, and the remainder section is everything else. This repeats in a loop. A correct must manage the entry and exit carefully. Go to slide 4. Uh, Requirements for valid solutions. Any correct solution must satisfy all three requirements. Um, simulate Similarly, uh, mutual exclusions. Only one process may be in its critical section at a time. Uh, these sections uh, give exits to only one person to enter in one time. Another solution is progress. If no progress is inside, the decision of who enters next must be made in infinite time. It cannot be delayed indefinitely. And third one is bounded waiting. Uh, limit exists on how many others may enter after a process request, so no process stops. There must be a limit how many times others can enter a process has requested. This prevents starvations. Uh, Miss even one and the solution is considered incorrect. Correct. Those three are requirements for valid solutions for critical problem. We go to on the slide. Uh, Categories of solutions. There are three categories of solutions: software-based solutions, hardware-based solution, and OS language level solutions. Software-based solutions. Uh, Algorithm approach in a user level code like Peterson's solutions, and hardware based solutions automate CPU instruction like provide provide by the CPU. This algorithm approach in in a sh- atomic CPU instruction like test and set and compare and swap. OS language level, high level abstraction that hide the low level details. OS and language level, high level abstraction like mutex lock, semaphores, and monitors are included in OS language level. Let's look at it. Uh, Peterson solutions. Peterson's solution is the two classic two process software approach. It uses two set variables, uh, flag flag which tracks whether a process wants to enter, and tron which indicates whose turn it is. Process pi sets its flag to true, gives priority to other process by setting tron is equal to z. It waits while the other process wants in, and it's their turn. Once the wait ends, pi enters on exits. It sets its flag to false. Flags to false. It satisfied all three requirements, but it's mostly conceptual today. Modern CPU do not of other execution which can break the flag and turn assignment. Its value is mainly theoretical. Hardware based solutions. Uh, Special CPU instruction make lock uh, executions atomic or single on entropycal steps. There is set and test. Set and test reads on memory locations and is to true in one step, returning the old value. If the old values was false, the process has acquired the lock. Another one is compare and swap. Uh, Compare and swap writes a new value only if the location still holds the expected value, otherwise it fails safely. Those forms the foundation of most real synchronizations mechanism. And now turn to operating system solutions. Uh, there are three solutions on operating system solution. First one is Motex Lux. Um, Motex Lux is a process called acquire before entering the critical section and release after simple and widely used. Semaphore. Um, Semaphore is an integer variables controlled by weight and signal. Uh, Binary semaphores like mutex counting semaphores manage a pool of resources. And third one, monitors. A monitor is a high-level construct, as in Java, that automatically enforces mutual exclusions. The programmer doesn't manage locking at all. Now on the slide, uh, we go to conclusions. To summarize the critical section problem, it's about safely sharing resources among concurrent processes. Any valid solution must guarantee actual mutual exclusions, progress, and bounded waiting. Those three are requirements of critical section. We covered three families about solutions: software-based solutions like Peterson's, hardware instruction solutions like test and swap, compare and swap, and OS level tools like Mutex, semaphores, and monitors. So, this is my presentations about critical sections, problem, and solutions. Hope you like my presentations. Uh, Thank you.